Okay, welcome to week 2, guys, and what is one lesson that should wrap up most of Algebra 2 for you. It has to do all about the parent functions that you learned all throughout the year. We're going to group them all into one place, talk about what the parents look like, a little domain and range, and then how to move them around with transformations. The good news is that you're not going to have to be, perfect when graphing these. In precal, it's more about a general sketch than it is knowing exactly which points things cross at. It's still good to know intercepts. Those are always important, maybe a vertex, but beyond that, it's just a general idea. So let's start with linear. Our linear parent is, of course, y equals x. And as far as what this one looks like, that's definitely just going to be your diagonal line that goes right there. The domain and the range on these, hopefully you still remember, it's all real numbers. And all real numbers can either be written as the capital R thingy with the extra leg, or if you learned interval notation in Algebra 2, you could do interval notation like this, where you say I'm going to negative infinity on the left, positive infinity on the right. Negative infinity down below, positive infinity up above. And that would be the same thing, whatever you like. I think I prefer these a lot of times, interval notation, but do whatever you want. Okay, the next parent we're going to go after is going to be quadratic. I'm just kind of going in order of, not importance, but difficulty. That would be a good way of putting it. Okay, so the quadratic parent is x squared. And you could probably sketch all these graphs without me. In fact, what you might try to do is, as I write the topic, if you remember the equation and or the graph, hit pause and actually see how much you remember. Try to figure out that equation, try to figure out that graph, try to figure out domain and range. And if you can do that, then you're awesome is what you are if you remember a lot of this, or you're going to know exactly where you're rusty. Now, the range is not all real numbers because this thing bottoms out at 0. So I would do that as 0 to infinity. 0 would have a hard bracket on it because you get to touch 0. Infinity needs a parenthesis because you can't land on infinity. So that's how I would do range. Okay, the next parent I want us to go over is, what do I want us to do? I guess next we could do cubic. And we're going to have a lot to do with cubic next week because we're going to talk about all the graphs that are x to the third, x to the fourth, x to the fifth. But now we'll just kind of talk about this one because I think you probably did a little bit with this last year. And it comes up a lot in precal and calculus. Alright, that's x cubed. Now, I made this a pretty drastic curve. It's not really, it's a little thinner than that actually, but I wanted you to really see what it was doing. The domain and the range on this one, it looks like all real numbers again, doesn't it? Okay, and so I'll just do all reals, okay? And in actuality, anything that has an odd exponent will take on that shape, and anything that has an even exponent like this will take on this shape, and it'll vary slightly, and more things can happen, but this, for a lot of them, this is a very true statement with even versus odd. Okay, the next ones that I would like us to look at are the inverses of the things we just did above. Okay, now oops, let's get rid of that. Okay, now this next one that we're going to do is actually not really an inverse, it's just interesting, and it does relate to linear. It would be the absolute value graph, absolute value. Of course, the equation looks like that, and the graph, you may remember, is a V. Now, why does this relate to linear? Well, it's the linear parent function, and what it's done is it's taken this bottom part of the graph that used to be here. I'll do it as a dotted line. That's the linear parent, but it's made all of these values positive because that's what absolute value does. So it's not an inverse, but it does relate, so I thought that was important to say. Okay, domain and range of this are going to be the same as your quadratic. all real numbers for domain, but only 0 to infinity for range. The next parent function, let's see if you remember, is square root. Square root. So there's the equation. Do you remember the graph? A lot of students do not remember the graph for this, but it's an awesome graph, so good to remember. It looks a little something like that. It stops at a dead halt at 0 and just barely kind of angles out and off to the side, almost like trajectory or something like that. On this one, the domain would be 0 to infinity, and the range would be the same, 0 to infinity. Okay, now something related, the reason I mentioned inverses, keep in mind that this one and the one above it, there is sort of an inverse relationship here. And if you can't remember what it means to be an inverse, if you were to draw the diagonal right here, don't write this on your paper, please do not write this. If you drew a diagonal and you took the red graph and flipped it over the diagonal y equals x, it would look like this, because these have an inverse relationship. Now the bottom half of it would not be there, and that's because, well, the bottom half's not there because we can't have negative square roots. Those are imaginary. So only the top part of the graph is actually there, but there is some sort of an inverse relationship. The said will be true between these next ones. If I took this graph, drew the diagonal y equals x, and I flipped the red across the green, then you would get this parent. And this parent is a cubed root graph, okay? So cubed root. Oh man, I wanted to be consistent and use the same color. Cubed root y equals the cubed root of x. And so with this one, like I said, we're going to take this red and we're going to flip it across that green line, and it would look like this. Whee! Alright, so that's a cubed root function. Domain and range on this are all real numbers. Even though it looks like the range might not be, over time it really will manage to grow all the way out to all real numbers. Alright, cool. So there's those parents. Hopefully you remembered a lot of those, or some of those. Now these are the next ones are the we hate these problem graphs, okay? There's just a couple more that we're going to do. I'm not going to do rational in this video. You know what? I am going to do rational. Why not? Blue. Alright, a rational function. Another one a lot of people don't remember. That was the 1 over x, okay? Y equals 1 over x. These can look like all kinds of weirdness. 1 over x squared was also a parent, but we won't talk about that one just yet. This is the one that was like, I know this is very untechnical, but I used to call this the swoosh graph. I thought of a Nike swoosh, and I don't really know why because it doesn't look like one, but I always called it the swoosh graph. This one was weird with domain and range because these were asymptotes. Asymptote here, asymptote here. So it was like everything except 0. So the way I like to write, there's two ways to write it. If you want to do everything except 0, you could either do this. I think this is probably ringing a bell for a lot of you. Negative infinity to 0, and then 0 to infinity. Okay, or here's another option for you, set notation. X is an element of all real numbers such that x cannot equal 0. And there I was on range, and I was saying x's, but let me change that to y then. Okay, y. Okay, this is called set notation. This is fancy math talk for the same thing as above. So whichever form you like, your teacher will accept. That's just kind of a cool notation to, honestly, just to show off if you want to be like, oh yeah, set notation, I'm fancy. You'll use that in college all the dang time. Okay, now we do the last two, which are the dreaded. That's why I saved them for last. Exponential and logarithmic. Yee. All right. There's so many options on these, it's like not even funny. There's actually 2 options. The parent would be if you have some number raised to the x, or on this one, log of some base of x. And these two are inverses of each other as well, kind of like that thing I mentioned earlier. What you'll have to do though is really look at your b, because if the b is greater than 1 or if the b is less than 1, you're going to have two different graphs, okay? So let's draw some I'm going to erase this because I need the room. Okay, let's draw our x and y axis for both we and yay and yay. Okay, now I'm not going to get like all crazy with how exactly steep they're supposed to be. That was algebra 2. That's when we get crazy with steepness. Here we're just going to notice, is that bigger than 1 or not? And then the bigger that number is, the steeper it is. That's it. That's all you really need to remember. What we're going to do is just get good at memorizing the parent and what it should look like. So for instance, if b is bigger than 1, let's say it's a 2, so 2 to the x, or 3 to the x, or 4 to the x. It's called an exponential growth function, and it looks something like this. There was an asymptote down here, and what I like my students to remember, there's an asymptote on the axis, and we usually cross at 0, 1. Okay, that's a good starting point, 0, 1. This is the same graph, except it's decreasing instead, so it's going to be a decay is what we call that. A decay function still has the same asymptote, still has the same intercept, and those are the parents right there. Like I said, it'll be steeper if these numbers are either bigger or smaller. Okay. All right, so now what about logarithmic? Well, now we take this graph, we imagine that diagonal I mentioned earlier, and we're going to flip it. So what happens is logarithmic, if this number is bigger than 1, it's a logarithmic growth, just like I said over here, and it looks like this. So everybody switched, which means this horizontal asymptote is now a vertical asymptote. And instead of crossing at 0, 1, we cross at 1, 0. So inverses mean x's and y's switch places, and so that's kind of exactly what's happened. So for this one, I'm going to take this graph and flip it and think, what would that look like? So once again, we now have a vertical asymptote, and it's a logarithmic decay. So it starts high and then decays. It goes down low. It decreases. That's another way of saying that. Okay, cool. So those are your parents. Now this was a lot of information in Algebra 2. Like I said, we just did the whole year on this one paper, but the good news is we just want to get good at, do we know the parents well enough, and do we know transformation form well enough to be able to graph these bad boys. So here's what I do. You probably haven't seen this way before. I kind of created it, but I like it. It works for me. Now, what I do is f of x is my function. So I'm going to do a generic formula. I'm not going to put this into a quadratic or an absolute value or anything like that yet. I just want to say, like, you have a function. I don't know what your function is, but the following are different things that could be done to your function. Okay, are you ready for this? This is where it gets fun. Okay, we could have a negative out front. We could have a number out front. We could have, let's go back to, that was black. Here's my function f. So this is if you have a negative or a number out front. And then my f of x, there could also be stuff inside, you know. So, for instance, eek. Okay, so here's what could be on the inside. There could be another negative on the inside of the function, another multiplier. There could be a plus or minus c. There could be a plus or minus d. So you've seen something like this, maybe just not written exactly like this, but over here I'm going to kind of talk about what my a, b, c, and d are, okay? First of all, if there's a negative in the front of everything, okay? So a negative out front of everybody is a reflection, and it's a reflection across the x-axis, okay? It's called a vertical reflection, but take note, I mean, that does mean across the x-axis. If the negative's on the inside of the x, on the inside of the function, it's the opposite, horizontal reflection, which means it's across the y-axis. Okay, so if you imagine that thing reflecting, that's why it's called vertical, because it reflects across the x, which makes it look up and down. This one makes it look side to side. Okay, now these others I'm not going to show an example. I'm just going to sort of write them all out. So A would be a vertical stretch or shrink. It's a dilation is what that's called. B is a horizontal dilation or stretch shrink. The C is a horizontal translation. So that just means left or right. Left or right. And if the number is being added or subtracted on the outside of everybody, it's a vertical translation, which means up or down. So, I don't know, like I said, I don't know how much you remember, but we're going to do some examples kind of that mix up all this junk with different functions just so you can compare it back to this and then see how it goes, okay? Now, I realize this is going to be kind of a long video, well, maybe another 5 or 6 minutes. So if you're bored and need a break, please take a break and then come back and we will apply all this stuff because we're going to apply it to each of these, okay? So I'm going to start, before I do anything else, I'm actually going to recopy for myself that formula that I had up here. Okay, so this is sort of my rule for myself of all the stuff that I could have, so that when I see a problem, I just compare it to all the stuff above. So for instance, if somebody gives me like negative x plus 1 squared minus 2, something like that. Okay, then what I would do is I would start with identifying my parent function, which that's why it's a quadratic, is because there's a squared there, and I actually draw my parent, or I sketch it, okay? Then I just go through my transformations. There's a negative out front of everybody, okay? So that's really important to between this one and this one, because like this one means it would be inside of yet another set of parentheses, which it's not, okay? So this is going to reflect it over the x-axis. So my first step would be that, and then I know I've handled that. Okay, now as I read this thing, I always go left to right. If you read these left to right and do your transformations in that order, left to right, then you're never going to be wrong, is what I used to tell my class. Go left to right and you'll never be wrong. So the next one will be my plus 1. So plus 1 is on the inside, so it's like this C. And when you're inside of parentheses, it does the opposite of what you think it's going to do. So instead of like a plus 1 actually does mean it's going to go left 1. Okay, so this part right here would pick up the red graph and take it to the left 1 unit. Okay, and then the down 2 on the, I just said it, the minus 2 on the outside would be like the D that's up here, which would mean up or down. A negative 2 does mean down. So for my last one, I'm going to go down 2. So 1, 2. Whee! Now, like I said, here's what's awesome about precal. Here's what you would need to know. You would need to know this shape is down in this quadrant, and you might be asked for the vertex. So what did we do? Left 1, down 2. We know the vertex, and we know the shape, and we're done. That's what's awesome about precal. Okay, absolute value. So let's make up a function that has an absolute value in it. So maybe it's like y equals 2, and then it's like an x minus 1, and then like plus 4. Okay, so now we know it's absolute value because of those bars. So we should start with the absolute value parent, which looks something like that. Okay, now I'm going to go left to right. Now that 2 is not trapped in parentheses. Okay, so it is a vertical dilation, which means that it's a stretch. You're going to be, it's almost like multiplying the y's by 2 is what's kind of happening. So when you multiply these y's by 2, it just makes it skinnier. Okay, so the bigger the number, the skinnier this is going to be. Then we'll do the next thingy, which is a minus 1. but that minus 1's on the inside. So once again, it's like a left or right. And since it's a minus 1, it's going to go right 1. Ooh, this one's getting a little cluttered. All right. And then my last step is the plus 4. Now that plus 4 on the outside is your vertical translation, so it does move it up 4. So this skinny blue V is going to move up 4. And honestly, because I'm overwhelmed with all these little graphs, I've got to erase this or my brain is going to explode. Okay, so what was I doing? Up 4. Okay, so it's going to look like that. So try to get that on there as best you can. But that's sort of what it's going to look like. Now your starting point or your vertex of this one is just 1, 4. And you could say that if you needed to say that. Okay? All right, now radical. An even radical. So this might be something like y equals the square root of negative x plus 1 plus 1. Okay, so I see this all the time. Actually, there's a negative on the inside of a radical, and people kind of wig out because they're like, oh wait, you can't have a negative on the inside of a radical. But you can if it's a function. I mean, this isn't a number, it can be anything, right? So what you got to do is just trust your transformations. Okay, start with your parent. Since it's even, it looks like that. Now, a negative under the square root is like a negative on the inside of the function. So this is the kind that's going to reflect it across the y-axis. So that would be my y-axis reflection. Then I've got next to that a plus 1 also under the square root, which means it's like it's inside the function. So it's going to go 1 to the, which way is that? Plus 1 would be to the left. So I'm going to take the red graph and shoot it to the left one. And then that plus 1 on the outside is, of course, the outside ones are easy, right? It's just going to move it up 1. So it'll look something like that. So you can erase all the old ones if you want, but that's what that graph would sort of look like. Moving right along, how about an odd radical? Okay, so same thing, except now we're using odd. So maybe it's like 1/2 cubed root of like 3x minus 9. Maybe it's this. Okay, so a couple things I need to say about this. If you're given this equation, first of all, if there's something in front of the x, but it's trapped inside the symbol, you really want to see the parentheses very clear like I have it up here. Okay, so there is a b, it's a dilation, but it can't be stuck to the x. You want to factor that out first, which is a rule that I would say like 75% of my students used to miss on a test. So before you do any graphing, you have got to take that 3 and factor it out. Now this looks like that equation above. Okay, you start with the cubed root graph, which looks like that. Okay, and now we start doing transformations. Well, there's a 1/2 on the outside, so now we have a fraction on the outside, which means it's going to be a vertical shrink. Now, a vertical shrink means I'm multiplying the y values by 1/2, so it feels like I'm pushing down on this graph and then pushing up. So it feels like I'm making it closer to the y-axis is what it ends up looking like. In fact, half is wide. See, the 1/2, half is wide. Now we got a 3 on the inside. Now that's a horizontal dilation. Now, when you're on the inside of something, remember how it's the opposite of what you think it's going to be? So it's not that it's making this like, oh, we're going to make this thing 3 times longer. It's actually the exact opposite. It's like you want to condense this graph into 3 times its shape that it was before, or I mean a third, I guess is what I should say. A third as big as it was before. So this is going to look weird because with this move, we are almost going to undo what we just did. So we're working with the red and we're going to squish it in by a third of what it was before, which makes it go back to almost what it was before when it was black. And I know that's weird, y'all, but that's how it goes. Okay, it really is. This is how it goes. So we've dealt with 2 dilations. got a little sketch going on here, and then the minus 3 would, of course, move it to the, what is that, right 3? Yes, right 3. So I'm going to take the squished green graph, move it to the right 3, and then I'll elongate it a little just to show that I do know it keeps going for forever. And if it's too cluttered for you, you know, we can erase what we had before, just so it's not ugly. Even that. Okay, so that's something that it should look like. Okay. All right. Whew, we're almost there. Long video. Sorry. Exponential, logarithmic. Okay. So exponential. I'm going to go ahead and do growth because you'll see that more than really anything else. So let's do 2, 3, x plus 1. Okay, let's say you see something like this. The parent is always the one where the base is being raised to the power. So it's almost like this part is your parent function. And 3 to the x, this number is bigger than 1. So I know that there's an asymptote here, and I know it's going to start by looking like this. It's an exponential growth. So that's how we start. Then we'll handle the 2 out front. So 2 out in front of everybody means a vertical stretch of 2. So I'm multiplying my y's by 2. And what's cool is when you multiply those y's by 2, that intercept of 0, 1, when you times that by 2, it's now up here. So this also moves your y-intercept. Okay? And that's something I used to use as a something like a trigger to help me out. So not only does it stretch everybody, it moves your y-intercept. And then whatever's up in the exponent, this is the same stuff as like your x plus or minus c. So if it's up in the exponent, it's like an x plus c. If it was down here at the back side, that's what would make it a d. So instead of being an up or down, this is a left by 1. I think I had an x plus 1 here. Is that x plus 1 or minus 1? Hard to tell. It was a plus 1. Okay, so that being said, left 1. So we're going to take red graph, move it left 1, which is this direction. So it's about right there. So now your y-intercept is changed. Okay, I get that, and that's okay. But if you're graphing using transformations, it was a good guide to use it to help us with the rest of this. Okay, and then my asymptote never moved. In fact, you might want to make a note that on these, the only thing that moves the asymptote is if you have an up or down. So moves the, so what is it, what did I say, up or down is the only thing that will move the asymptote. Whereas on a logarithmic, the left, right translations will move the asymptote. Sorry about my handwriting. My students always tell me I should be a doctor because I have terrible handwriting. Okay, so let's make up a logarithmic one. How about y is equal to, ooh, gray. I didn't even know I had gray. That's exciting. How about log of x plus 5 minus 1? Okay, so let's say we have something like this. Okay, the plus 5 behind the log is going to be my left 5. This is on the outside. It will be my down 1. So I know I just need a log parent, and I need to move it left 5 and down 1. Well, the log parent, if there's no base written, what's the invisible base? Do y'all remember? It's actually a 10. So it's definitely greater than 1. The same thing as if you see a natural log up here. Please remember the base of that is e, which is also bigger than 1. So both of these parents are very similar. You've got your asymptote on the axis. It crosses at 1, 0, and it looks something like that. Okay, so there's our parent, and then we just go, what'd I say? Left 5 and down 1. So let me move the graph left 5 and down 1 first. So left 5. 1, 2, 3, 4, 5, and down 1. I don't like that. It's too, it's running off into no man's land. Okay, let's try that again. Let's let that be 1, 2, 3, 4, 5. Okay, so 1, 2, 3, 4. Okay, so the point moves there and then down 1. So the graph, this gray graph is going to end up here, like this point just moved here. I'm going to recopy the gray. Look at your asymptote. It's no longer at 0. It also shifts back 5. And that'll help guide. It'll help guide you if you go ahead and re-sketch that asymptote and then sketch your curve or whatever you need to do, but it helps guide it if you let yourself know where that asymptote is. So the homework, you're going to have a big sample of all different kinds, and I already know which ones are going to be tough. Not going to tell you yet. Just good luck with it. Watch the solution video. We'll do lots of practice with this and even more stuff in tutorials.